So as before I start with the lecture, I just want to inform you that different Moodle page has been created for the group, and this Moodle page is basically going to be common for both the MTech and the BTech students. So we will not be using the older groups that were created. Okay. I think there was a Moodle page separately for MTech and separately for BTech, so we'll not be using those two Moodle pages anymore. A combined one has been created, and I am in the process of uploading the lecture notes and the links to the YouTube lectures. These YouTube lectures are in the unlisted mode. Only if you have the link, you'll be able to see. So that is where we'll be operating. Okay, so your exams, assignments, everything will be in that particular page. Now, I'm just preparing an assignment. I have prepared simulation exercises. So I will be uploading them today, probably after the class is over. Let me just show that. And okay, so I'm giving you two simulation exercises. All right. One is basically a current mirror exercise. So both of them are basically current mirrors. The first one is a simple current mirror.
Sir,
My voice is breaking.
Yes, sir.
Okay. I don't know. I am in the institute, and even yesterday we had some internet issues in the afternoon. I don't know. How is it now?
Now it is looking fine, sir.
It's the same, or it's better? Okay, fine. Okay.
But like
All right.
small
So
breaks are.
I see.
Your voice
I
is
am
not consistent.
My voice is not consistent. Okay, let me just maybe speak for another minute or so. Let me know how it is. If not, I'll see what I can do. Are you able to see my screen?
Yes, sir.
Yes, sir.
Right. Okay. Yeah. So I will upload this in the Moodle page. So there are two simulation exercises. So both of them you use LT-Spice, use the 180 nanometer file that has already been given. VDD, take it to be 1.8 volt. Sometimes students, start trying to play around with VDD. Don't do that. 1.8 is fixed. Okay. The first question is like you have a reference of 10 microamp. You need to generate 100 microamp from this 10 microamp. Okay. And this 100 microamp current source, which is basically mirrored, has to be one end is connected to VDD and the other end is connected to a block below it. So basically, you need to have a PMOS transistor pumping the current. Okay. And so all the other things are there. You can go through it. Same way, the second one is a low voltage cascade current mirror. This is a NMOS current mirror because I have mentioned that the mirrored current needs to sink 100 microamp. One terminal is connected to ground. And I've given some specification. You can use any of the low voltage cascades that is possible. And I also want you to use a DC operating point and calculate the output impedance. Right? We derived it in the class yesterday in terms of GM and R0. And I want you to extract the GM/R0 parameters from the DC operating point. And I also want you to calculate it, from the graph, compare the two values. Both should actually match very closely. Okay. I'm also trying to give you some practice problems. If I don't get to the practice problems by today, at least the other stuff I will do. So these two simulation exercises will be towards your grading. Okay, you have your internal marks, and as I mentioned, so some of you might not have been there for the first class. I mentioned that this course has a 40% internal credit. Okay, so 40% is for course project and internal marks, and these two simulation exercises will be graded towards that. You have 2 weeks time to submit this. The time starts from today, so which means that today is the 10th. By 24th September, these two simulation exercises are due to be submitted. So don't wait till the end. And the reasons why I give this simulation exercises is because you actually do your learning by running simulations and designing circuits. Okay. That is where your real hardcore learning happens. Okay, so please take it seriously. Don't try to copy from each other. Don't share schematics from each other. You try to fool me, but at the end of the day, you will not learn your subject. Okay, so do it on your own. If you need any help, sometime next week, you can ask me in next week's classes. Whether if you have any clarification or if you are stuck at some point, you can ask me and I can do that. I'll help you. I'll also give you one more simulation exercise. Both will be due on 24th, which is basically, the basic device characterization, which is ID versus VGS, very simple plots. So both of them will be due by 24. All right. So I will upload them by today. Now, the set of practice problems that I will be giving, they don't need to be submitted. Okay. Those are mainly for you to understand the subject even better, and also, it might help you in your exams. So I'll give them as well. Okay. All right. Let's get into the class now. Yeah. So how's my audio now? You guys are able to hear me clearly, or is it still breaking?
Breaking, sir. Breaking between.
Okay. Okay. Let me do one thing. I'll. Are you guys able to hear me now?
Yes, sir. Seems fine, sir.
It's fine. Okay. All right. Let's try to work with this. Give me a moment. Right. I hope the audio is. If not, just let me know, please. Okay. So till class, we were looking at current mirrors and current sources. We looked at output impedance. We looked at cascode current mirrors. We looked at, when you talk about current mirrors, so far we have talked about these two issues. One is the systematic offset. Now, what is the systematic offset? This is basically due to VDS mismatch. Okay. And also the role of R naught comes into the picture here. But secondly, we also talked about the output impedance. Okay. So if you have a high output impedance, it minimizes the effect of systematic. Okay, let me not call it offset. Let me just call it systematic error. That would be the right word to use. Okay, systematic error. And we also looked at output impedance. We saw, how cascoding improves both of them. Right? So when you have some small signal variation at the terminal of your current source, having a higher output impedance makes sure that the current remains quite rigid and fixed. Okay. And also we saw that when you have systematic error, like when you do cascoding, the systematic error also gets minimized. Now today we are going to look at two other sources of error, or two other ways by which your current mirror can get screwed up. All right. Now the third one is what is called as gradient errors. All right. Now it is important for you to have a very clear understanding as to what we are talking about. Okay. Because these are all so many different things. Sometimes they may look a little similar, but their origins are different, and the solutions to solving them or to mitigate their effects are also different. Okay. So you should be quite clear. Many times what happens is not only students, but even many engineers kind of get confused between these different sources of error. Now, what do we mean by gradient error? Now, if you look at the CMOS manufacturing process, right? Some of you are taking, you've already taken course in your previous semester. The VLSI technology, things get fabricated, right? So you know there's like so many different steps which happen. Now, when these things happen, although you try to have them as controlled as possible, certain things like being certain things, are just like there is a limit to which you can control things. Okay. Now, what happens many times is that let's say this is your
Sir,
Yes. Yeah.
your
Someone
Your
voice.
voice is breaking.
Okay. So I don't know what to do. Uh, I thought it was maybe my headset was having a low battery and they changed to my laptop's mic. I think it's the internet which
Sir, you
is
can try
in
rejoining
campus.
once,
I didn't
maybe
notice that it was bad.
it might help.
Okay, maybe I can do that. Okay, let me do that. Yeah.
अरे फिर स्क्रीन से नहीं होगा ना बग की वजह से
कौन सा बुक?
कल बोल रहा था ना सिटीज कुछ सेकंड टाइम नहीं होता स्क्रीन शेयर ऐसे कुछ
सर
Okay, so how's my audio now? Are you guys able to hear me clearly or it's still bad? Okay, let me try. So I guess the recording is going on. All right, let me share my screen and get started. All right. So to continue, we were looking at, so I was mentioning about how the VLSI processes, the manufacturing processes, there you usually end up with some kind of errors in the process, right? So if you say that this is the x-axis dimension, okay, of the chip. So let's say you have a wafer which is like this. Let's say the wafer is some 8-inch wafer or 12-inch wafer or something. That's your silicon wafer on which you have multiple chips or multiple copies of your IC, right? Now, what happens is when it goes into your different processes, like maybe you have your diffusion happening, you have your polishing happening, you have you kind of heat it up and all those things happen. Now in some of the processes what can happen is there can exist certain gradients along the x-axis, okay, or there can exist some gradient along the y-axis. In fact, can be along any axis which can be decomposed into a gradient along x or y axis of the silicon. So which means, for example, if you were to plot the, let's say the, for example, the doping concentration. All right. What can happen is, when I say the x-axis, it's a physical distance. Maybe when you go from this end of the wafer to the other end of the wafer, your doping concentration might have a small gradient like this. Okay, or it can also have a negative gradient. In fact, the doping concentration may go from kind of be in that particular angle also it might have a gradient, which can be decomposed to a certain gradient along the x-axis and a certain gradient along the y-axis. All right. Now, this routinely happens in ICs. So, which means that what happens pretty much at a kind of a wafer level, when you come to, let's say, one IC that you're having, okay, and you kind of blow it up, okay, and you say, okay, from left to right as you go along the x-axis or along the y-axis, you end up with certain types of gradient. Okay, so which means that why are we talking about these things? It's because, for example, let's say you are having a current mirror. Let's only talk right now about a simple current mirror. Okay? Let's say this is, let's call this transistor as A. Let's call this transistor as B. All right. Now, let's assume for now you want, let's say these both are, you both to have the same current. Okay, so you have a certain IREF coming here and you want I out expected to be equal to IREF. All right. Now, the way that you would do a layout, I have shown you the layout in one of the previous lectures, right? So let's say this is your transistor A, and let's say your transistor, this is your transistor B. Let's say this is transistor A, this is transistor A and transistor B. Now, as I mentioned, sometimes you use fingered devices or you use multipliers and so on. So, for example, let's say we use for this example we have two multipliers of A and two multipliers of B. Now, let us say you have laid out your transistors, you have done your layout like this. Okay. Left hand side A transistor, right hand side B transistor, and of course you do all the regular connections. So let's say this is drain and source, you do all the connectivity. Let's assume that all the connections are done appropriately. Now what happens is we have mentioned that on the IC along the x-axis there is a certain gradient. Okay, so in fact at this particular level, I mean you have just a small slope. Okay, you're not going to have a very wide, gradient. You just have a little bit of gradient. Okay, let's say the doping of this particular transistor is slightly lower than the doping concentration at this particular transistor. There's a little gradient which is probably, it is looking like kind of like this. There is a slope. Now what will happen? So at the end of the day, when you write circuit equations as circuit engineer, you don't write equations where you talk about doping concentration and this and that, right? You ultimately bunch everything together and then say, okay, there is a certain mu and there is a certain C ops and there is a certain threshold voltage. Now what can happen is the threshold voltage of, let's say, for example, the threshold voltage of, let's say, A1, threshold voltage of A2, threshold voltage of B1, the threshold voltage of B2. Now, because of the way in which the gradient happens, it can happen that it can be in this order. Conversely, it can also be in the other order also. I mean, depending on how the gradient exists. Okay. Let us, for example, just take the case where the left-hand side transistor has the lowest threshold voltage and the right-hand side has the highest threshold voltage, but it kind of gets captured effectively as having a gradient in the threshold voltage. Okay, let me pause at this point and ask, how is my audio? Is it still breaking up or is it better?
Fine, sir.
No, it is fine. Great. Okay. Recording is going on, right? Because I stopped the recording on my laptop as well.
Yes, sir.
Yeah. Okay.
Yes, sir.
Thanks. Yeah. All right. So now what has happened is due to something that has happened, maybe the polishing, there is a certain gradient in the, CMP that is happening or diffusion or in the lithography, something has happened, but you get a certain thing. And this has been observed consistently in many ICs. So what will happen? In this case, your reference transistor is going to have the effective, let's say VTHA is going to be less than the effective VTH of B. So which means that although you're giving the same gate to source voltage, the current I out is not going to be equal to IREF. Correct? This effect is what is called as gradient error. Okay. Now this gradient error can happen in any direction, which can be decomposed, as I mentioned, along either the x-axis or the y-axis. Now how will you solve the problem? This is a problem. Can you just look at this and tell me how can you, let's just assume that the gradient is linear. This is an assumption, but it's a fairly decent assumption. Okay. Now, how do you think we can solve this issue? Any ideas?
Place the component perpendicular to gradient.
The gradient is, let's say the gradient actually, as I mentioned, is in some kind of direction like this. So which means that in x-axis, you really don't know in which axis you're going to, you really don't know in which direction it is going to happen. Okay. Only thing is it is in some arbitrary direction, which can be decomposed into a gradient along y and a gradient along x. Okay. So, in fact, this is one wafer. Maybe the next batch of wafers, when it comes, the gradient in its direction. Okay. So that's a highly random thing. You really don't know, right? Just I've given you a kind of a clue that the gradient is linear, which means it's like a, it's a straight line with a certain slope. Can you rearrange the layout in any way? Can you think along those lines?
Sir, what do you mean by rearrange?
AB, sort of.
Okay, if you put AB, let's go to this one. Let's say if you put AB, still this is greater than this is greater than this, right?
AB, BA then.
Very good. So either you can go AB, BA or BA, AB, right? Right. If you do this, what happens? It's like if you have a linear gradient along the x-axis, let me just write it down here, linear gradient along x-axis gets cancelled, right? So this type of layout is what is called as common centroid layout technique. Okay. Now, whenever you have current mirrors in the industry, whenever people design current, of course, current mirrors are used in pretty much all analog circuits. So you basically what they will do is you will have one big circuit and you'll have a bunch of PMOS current mirrors. You'll have a bunch of NMOS current mirrors. Usually they will say, okay, all the current mirrors put together, you will do a combined layout, and they will be common centroid layout. Okay, because why is it called as common centroid? The centroid of transistor A is what? Here, right? And what is the centroid of transistor B? It is here. Okay, so it basically means that whatever, even now, let's say you are mirroring this to another transistor C. Okay, so you will basically do it in such a way that the centroid of transistor A, centroid of transistor B, and all the, basically this means that the centroid of all transistors are the same. All right. Now, when you have a large circuit, when you have multiple transistors being mirrored to, you will basically have you have to think a little bit and do a more careful layout. Now, many times it need not be, and it also will be like that you have a certain ratio also. For example, if you have a 1:2 ratio, now what will you do? You'll have A, then you'll have B, you'll have B, you'll have B, you'll have B, and then you'll have A. Now here again, the centroid of A and the centroid of B are co-located. All right. So like this, you will have different techniques. Now you can also do a 2D two-dimensional. So here you had transistors only in one direction, right? Like all the transistors are kind of stacked up, next to each other. It need not be the case always. Okay. Sometimes you will basically have a kind of a two-dimensional layout. Okay. So for example, you have A, B, you can have B and A. So now you have to talk about the centroid and let's say you put four transistors, 4 units for each. Okay. So it becomes like this. Okay. Let's say you have 4 units. Now what happens is the x-axis centroid. So if you see, if you look at the x-axis as well as the y-axis, in x-axis they should have a common centroid. Y-axis they should have a common centroid. Now you can see that in the x-axis case you have a centroid like this. The y-axis case you have a centroid like this. Basically the whole 2D structure has a common centroid. Okay. So doing current mirror layout usually is done very carefully, and you always use unit cells so that each of these boxes that I have drawn, they are all of the same dimensions, same W and L dimensions, and you have to be quite smart in the way that you do. In fact, it need not be a 2 cross 4. It can be a 3 cross 3, 4 cross 4. Sometimes, when you have so many transistors, it becomes a very big thing. And, sometimes you will have like 1:3. For example, if you have a 1:8 ratio, okay. So then what you will do, you will have A in the center, and then you will have something like this, in band gap references and all, you do the layout something like this. Okay. So you might have a 1:8 ratio. You have to kind of think about it. Make sure that the centroid is the same in of the whole structure. The centroids are co-located. That is important. Okay. So gradient errors. Yeah, somebody has a question. I think someone's mic
Yes,
is
sir.
unmuted. Yeah.
Sir, what if the ratio was 2:3? Means there there were odd number of A's or B's
Yeah.
compared to.
Yes, you have to make sure as much as possible it is common centroid. Okay. So yeah, 2:3. There are some tough ratios, but usually you don't have. Yeah, it can happen. Nobody can say
So
it
we
can.
can
Yeah,
we can
sorry.
keep the three. We can keep the three part like in a corner of
Yeah, you
triangle.
can you can do like this, right? Let's say this is
Yes, sir.
B, A, right? Something like this.
Yes, sir.
Yeah.
Sir,
Yeah.
I have a very naive question. How exactly are we trying to cancel out using this centroid theorem? You told that it is the linear doping concentration.
Correct. Correct. Yeah. So, if for example, if you take this case, let's say the VTH of this is going to kind of, it'll average out, right? Like if you take the average of the VTH of this and this, and you take the average VTH, it will come to be the same because you have a linear gradient. You're assuming a linear gradient.
Okay, sir. So we want it to be symmetric so that the VTHs will get a
Will
same
be the
value.
same. Yeah.
Okay.
Yeah. Okay. You want to make sure that, okay, again here the VTH of B1 will be in this, order, but then the average VTH of the whole B device, right?
Yes, sir.
The
Okay.
average of A and average of B will be the same, which means you'll get the same current.
Okay, sir.
Okay. Yeah. All right.
Sir,
So this is what, yeah, someone else had a question.
the gradient it may not be necessarily linear, right?
You're right. It may not be necessarily linear. It can also be non-linear. But I think what they have found experimentally is that taking care of linear gradient itself solves the thing to a large extent.
Okay, sir.
Okay. Yeah, but I think what they have found is that it is predominantly linear. Okay. So a big chunk of the problem is solved by, as you may, I mean, doing this common centroid. Yes, there will be some delta, which you cannot do anything about. Okay. But if you don't do this common centroid, it's going to be even worse, much worse. Okay. So that's the logic.
So while we are designing, one question while we're designing A, for example, we fix onto one VTH value, but as we try to do the layout process, the VTH will shift a bit. So we need to design the current mirror for that VTH, right, sir?
No, not at all, not at all. Okay. So this effect you will never see in simulation.
Okay.
Okay. When you're running simulation, even when you do layout, and you'll do what is called as layout parasitic extracted simulation. That is to say, see, in schematic, you assume all the wires are ideal, right? So if you take this current mirror, you have a lot of wires, right? You have wire here, this connection, all these connections. In schematic, it's an ideal wire. But when you do layout, all these wires are strips of metal which have some resistance and some capacitance both to the substrate as well as to adjacent metal layers. Now all those effects are captured by what is called as parasitic extraction. Okay.
Okay.
And then you run simulations again with those parasitics extracted, which means that the tool itself will tell you, okay, how much resistance is there on each line, how much capacitance is there, and other things. So based on that, you will basically run your simulation again and then see how the effect is. But in all these things, you don't see any gradient error. Okay.
Okay.
This is something you will see purely in experimental results.
Okay. So we cannot model it in a simulator.
No, you cannot model it. So you only have to use your, logical sense to say that, okay, if there is some gradient where it has a component along both x and y axis, I have done a layout in such a way that the linear gradients are taken care of.
Okay.
Okay.
Sir.
Yeah. Now there is one more thing also that people do. What happens is when the fabrication happens, and these edges can get a little distorted. So basically, especially in the polishing processes, these edge transistors can get slightly affected. Okay. I mean, you have a transistor like this. I mean, this thing can become little, I mean, usually this will be jagged if you try to use maybe, I don't know if it's a SEM or a TEM, that is either a scanning electron microscope image or a transverse electron microscope image. You will see that you are not going to have very sharp, clean-cut lines. You will have some jaggedness. But what happens is, especially these edge devices will have some more jaggedness, because that is where the polishing comes, and when your polishing comes, that is where it hits this thing, right? So in order to, and that can impact your current a little bit, okay, because now your width and other things are getting affected. Now because of that, what they will do, they will put what is called as dummy devices. Okay. If you look at all these current mirror layouts, especially sensitive analog layouts, they will put some dummy devices. In fact, if you have a two-dimensional thing like that, you will have dummies all around, basically. Okay. So that like in both directions, when you are coming with all this polishing and other things, the dummy devices, the gate and the source and the drain will all be connected to ground. Okay. It's a totally a dud device. Okay. It does nothing. It's basically like a sacrificial device. It sits there taking all the blows, makes sure that your actual device is protected. So you basically have dummies like all around like this. Okay. And usually you will see that a ring of dummies all over the place. Okay. So these are the things that can go wrong. So we looked at gradient error. Now this gradient error is different from process variation. Okay. Process variation is when the whole wafer will become either slow or fast. All right. Here it is like one, I mean, like this, let's say you are taking this IC, all the transistors in that IC become, have a lower threshold voltage or a higher threshold voltage, or, that is how we model. That is called process variation, which we saw earlier. Okay. Here, what we are talking about is
inside the same IC, if you go from left to right or from top to bottom, the threshold voltage shows a certain gradient. That is what we are doing. Now beyond this, there is one more fourth effect which I want to talk about, which is called as random mismatch. Okay. Now, as the name suggests, it is random in nature. Okay. So which means that, let's say you put two transistors. Let's just call them, A and B for now. No matter how much effort you take, okay, you put them close to each other, you put dummies around, you put, let's say you do common centroid layout, okay, let's say, you do something like this, all the effort you take, still there will be mismatch between two devices, okay. Now, why it is happening? It is because of the it is what is called as random dopant fluctuation. Okay, sometimes acronymized as RDF. Okay, which means that it's a random variation. You can't do anything about it. Okay, from the process side, people who work on all this VLSI fab related equipment, they do their best to make it as consistent as possible. From the circuit side, we try to make it as foolproof as possible. Still, you end up with some threshold voltage changes, okay, which basically exist. Now, this random dopant fluctuation, one way to understand is basically, as the name suggests, the doping concentration, all the layers that you do, there is a fluctuation between device to device. So, which basically means that there are no two identical devices on a chip. Okay, now please notice that gradient errors and RDF or random mismatch happens inside the same IC. Okay, transistors inside the same IC. Whereas this is different from process variation where the entire wafer is affected. Okay, the entire wafer, all the transistors go up or all the transistors threshold voltage go up or go down. Okay, that is different. RDF is different. Gradient error is different. So please make sure that you understand these things very clearly. Okay. Now, why is this? So if you look at this particular gate, okay, I have drawn in a very bad way, but if you look at a textbook, if I were to draw it, I will draw it as a perfect rectangle, right? Okay, the gate, for example, okay, let's say this is my gate. Now, when I'm doing my layout also, the other day I showed you layout, they all look like perfect, proper rectangles, right? But after fabrication, especially for small channel lengths and so on, if you look at a transverse electron microscope, the way that this rectangle will look like is something like this. All right. It is not a perfect rectangle. It will have some jaggedness. Okay. Now, correspondingly, what happens is that this jaggedness of this transistor and the jaggedness of the other transistor will not be the same. Okay. So you can talk about an effective W by L ratio, which is being different between transistors A and B. Okay. Again, this is something that you would see in simulation. And also what happens is these things are statistically modeled. Okay. So what they will do is the foundry, when it is coming up with a certain technology node, they will, run these devices. Let's say they take some 1,000 devices, 10,000 devices, and they will characterize each of the devices. And let's say they estimate the threshold voltage. And what will happen is within the same die, the mismatch is kind of characterized. Okay. So basically you end up with the mean value, which becomes your nominal, and you also end up with a standard deviation. Now the standard deviation is different from process variation. Okay, this standard deviation is the variation within the same die for the same process corner. All right, for the same process corner, there is a mismatch between multiple transistors. Now, if you kind of think logically about it, okay, let me say I have one device which is like this and another, oops, okay, and another device which is like this. Okay. Now, if you were to talk about delta W by W and delta L by L for, let's say, device 1 and device 2, where the dimensions are different, which of the two will have lower variation?
Second.
The second one, right? Why is that the case?
Delta L will be almost similar for both. L will be more for 2.
Very
So
good, right? Because of the lithography limitation, limitations, basically the delta L or the delta W, whatever you see here, will be the same for both the devices, but whereas the denominator is different. Okay, so what can we expect? We can expect that as the area of your device goes up, what happens? The variation comes down. Okay, now this is true not only for transistors, this is true for resistors and capacitors also. Okay. Now we saw how resistors can be implemented. It can be diffusion, poly, whatever it is. At the end of the day, it is on rectangle, right? A rectangle element where it's a rectangular diffusion, rectangular poly diffusion, or whatever it is, right? Some material which gets fabricated in a particular shape, and this shape is going to have some jaggedness, some randomness associated, and the more you increase the area, the lesser the impact of your this one. Okay, so we define what is called as the standard deviation of, let's say, delta W, or for example, what happens is, let's say, delta VTH of a transistor, it has a certain coefficient which is called as the Pelgrom's coefficient, okay, divided by root of W into L. Okay, in other words, basically we are just saying the sigma of delta VTH, okay, is nothing but is inversely proportional to the root of area. Okay, so now when you take a current mirror, for example, I'm just explaining these things with current mirror. We'll see, there are other circuits also where we do that, where let's say you want an exact copy of the current, or you want an exact scaled copy of the current, right? And you have this variation coming and affecting you, and as you go for smaller and smaller transistor nodes, the jaggedness becomes more, and therefore the sigma kind of becomes more. Of course, the technology also keeps improving. The only solution to this RDF problem, the random dopant fluctuation problem, is to increase your area. Now, in simulation, how can we see this result? Now, in normal schematic or layout extracted simulation, you will not see this effect, but we do what is called as a Monte Carlo simulation. Now, what is a Monte Carlo simulation? Now, some of you who might have kind of delved a little deeper into statistics know that Monte Carlo is one of the statistical, simulation techniques. Basically, what it means is the foundry would have already, measured a large number of devices, and they would have come up with this mismatch model, okay, where this Pelgrom's coefficient is extracted. All right. Now, the same thing you will see even in delta R by R. Okay, for a resistor, you will have some A delta R by R divided by root of W into L of your resistor. Okay, same thing for capacitor. All right. Now, any of these things, when you have mismatch, this Pelgrom's coefficient is extracted, and these things are modeled. Okay, these things are modeled, and therefore what happens is when you run a Monte Carlo simulation, it does what is called as Monte Carlo sampling. Typically, you might run some 200 runs or 500 runs. Some people run even more, some 1,000 runs. Okay, what happens is, let's say I have a current mirror. Okay, what happens in a Monte Carlo simulation is I'm going to simulate it, let's say 200 times. But every time I simulate, it is going to sample in a given space. Okay. Now this Pelgram's coefficient basically gives you the sigma, right? So if you look at the thing, this is your mu and this is your sigma. Let's say this is your mu VTH and there is a certain sigma. And now what happens is every time you run this simulation, it's going to pick a pair of points within this Gaussian curve. Okay. And it will pick a point, randomly it will pick points and you'll run it, let's say 200 times or 500 times or 1000 times, how many ever runs you give. Now what will happen is this kind of mimics what you would get after fabrication. Okay. And so what happens is when you plot the I out, okay, as you expect, you will basically have a Gaussian response. You will have a I out mean and you'll also have a certain sigma of I out, which typically will be Gaussian in nature. In fact, when you run 200 or 500,000 points, whatever it is, your cadence tool will be able to plot the histogram also. You can plot the histogram and you will say basically, you know, this much is the thing, this much is my sigma and so on. Now, if your sigma is too much, okay, if your sigma is too much, what can you do to reduce the sigma?
Increase
Let's
the
say my
area.
sigma I out. Yeah, how can you reduce the sigma I out?
Increase the area of transistor.
You'll increase the area. Yeah. Okay, for let's say your design one had W equal to let's say 5 micrometer and L equal to 180 nanometer, and you are not happy with the sigma, you will go and do what? Design 2, where you keep the W by L ratio constant, but what you'll do is you'll just scale up the W and the L. Okay, so let's say you increase it by 3 times, you get 540 nanometer and you get 15 micrometer. Now what will happen? Your area increases, right? Your sigma comes down. Now the additional benefit that you get is your R naught also becomes higher, right? That we have already seen. So increasing area, it has the advantage of lower mismatch. Okay. L increase gives rise to R naught increase. And we will also see later that flicker noise goes down. Okay. So for random mismatch, this is the only solution. Okay. They basically go and increase your area. Of course, when you talk about offset and so on in terms of op-amp, there are other techniques to take care of offset and other things. Like there's a technique called as chopping, you have offset cancellation, you have, you know, other techniques like that. But for things like current mirrors, where you cannot do anything else, you cannot, you know, do chopping, you cannot do, you know, other switched capacitor based offset cancellation techniques. The only thing that you can do is to increase your area such that your sigma I out comes within tolerable values. Okay. Now, given the sigma I out, you can also calculate it in terms of percentage and see how much percentage you are getting. So with this, I'll conclude today's class. Are there any questions, any doubts? So just going back to the first slide that I had. So in current mirrors, you have all these issues. You have systematic offset, a systematic error, the output impedance, which determines, you know, how much your output voltage changes your current. You have process variation. Of course, process variation is taken care of by current mirrors. You have gradient errors. You have random mismatch. Okay. Now I have explained these concepts, especially gradient and gradient errors, random mismatch, and other things in the context of current mirrors. These will apply even in the context of other amplifiers, op amps, and so on. Any questions? Any doubts?
Sir, usually we take like W will be around 10 times or 20 times L. So why is it like that, sir?
We take, okay, that is in order to for you to get the required current. Okay, you
sir.
can keep W equal to, so usually what happens is there is a W min and an L min. Okay, the other day when I opened up the model file, I think W min was around, I forgot, was it some 270 nanometer or something? I'm not very sure. It might be, and L min is basically some 160 nanometer for a 180 nanometer process. Okay, so first of all, you start off with this, and then what happens is in your ID is proportional to your W by L, right? Now, for a given gate to source voltage, you have to scale your W by L to get the required current. If you keep the W by L ratio the same, you have to go and scale up your VGS minus VTH. Okay, this is the square law model. Of course, modern transistors, they don't have a kind of a quadratic response. It depends on where exactly you are, right? So you might end up with having to have a larger gate to source voltage. So it is a trade-off. It's a trade-off between your gate to source voltage and your W by L ratio.
Okay, sir. And also, sir, like in the if we are seeing a current mirror, the
Yeah.
transistor which is associated with the reference current, we can
Yeah.
keep the L of that lower also, right? It will not affect the reference current that much. Like we are
Yeah.
operating at one point only, so it Arnold will not have that much effect on that. Can we
Okay.
do like that?
So yeah, I understand what you're saying, but I want you to go maybe 2 lectures back. And when we started looking at current mirrors initially, I mentioned that you always keep the channel length constant across the entire current mirror. Okay, because you have a drawn length and you also have the diffusion under the oxide, right? Like if you have a this one, your oxide does not exactly end here. Okay, your oxide will be something like this. Okay, or rather your diffusion will not end here, your diffusion will be something like this. So if your L drawn is this much, okay, you have some LD, let's call it as LD, which is the overlap part. So the L effective is given as L drawn minus 2 times LD. Now when you scale lengths, right, the LD remains constant, but your L drawn keeps changing. So you don't get the exact W by L ratio. You just go back, I think, I don't know if it is 2 or 3 lectures back. We have discussed this particular aspect. And secondly, this is one effect. The other effect is the threshold voltage is actually a function of the channel length also for deep submicron processes. Okay. So it can happen that if you do, let's say, a lower channel length for your left hand side transistor and a higher channel length for your right hand side transistor, you will end up with a different threshold voltages for both of them, even in schematic simulations. Okay, which means you will end up with current errors. Now there is also another aspect. Just now we talked about it, right? When you have the area different, then obviously the variation mismatch between transistor A and B will be very high. Correct.
Yes, sir.
So there itself you get completely screwed up, right? Like you will have some current on the left hand side and totally different current on the right hand side. Okay? The
Okay,
mismatch will literally kill you. So for all these different reasons, it is like a complete no-no in the entire analog IC design community to ever change the channel length. You change the channel length, you change it for all the devices. Okay.
Okay, sir.
That's
Okay.
that's like the holy grail of things. You don't touch it because of all these different issues that you will encounter the moment you have different channel lengths.
Okay, sir. Sir,
Okay.
what is the accuracy we expect for these devices, like while current mirroring or something?
Okay, so it varies from process to process. Some of the processes might have larger Pelgram's coefficient, some might have lower Pelgram's coefficient. Again, for a given Pelgram's coefficient, for a given process, okay, you can always keep increasing the area till you satisfy your sigma I out. But yeah, I mean, it's different. Okay, I really don't have a number in hand, but typically, when you talk about ADCs or D to A converters, digital to analog converter, what happens is what there is something called as current steering DAC. Okay, current steering D to A converters. where basically you have a reference current and you have binary weighted copies of the current. Okay. Now, for current steering DACs, you are limited to kind of around 10 to 12 bits of resolution. Beyond that, you cannot really help with your mismatch. So there is a kind of a limit, but I really don't know such a number offhanded. Typically for current steering DACs, where basically you depend on perfect matching between current sources, you are limited to around 10 to 12 bits of resolution. That's how it is.
Okay, sir.
Okay. Yeah.
Sir, so basically here we are having a trade-off between area and the mismatch, right?
Perfect. Yes. The downside is area. Yes. The downside is basically, let's say, first of all, you have large area. You will see that sometimes these current mirrors will occupy a very large, big transistors will be there. And secondly, they also increase, because of area increase, you'll also have capacitance increase. Okay. So for example, if you have let's say, a differential pair biased by a current source like this, and you are trying to increase the area of this transistors, what happens is you are now putting a significant amount of parasitic capacitance at this particular node. So area is more, capacitance is more, and all these things, of course, everything has a trade-off. Okay, any other questions? Good observation. Yeah. So there are situations where, for you to have a very exact copy or an exact scaled copy is more important than just saving area. So you just go ahead and, increase the area till you get what you want. Okay, so if there are no other questions, we'll wind up the class today. I'll post the assignment, the simulation exercises. Both the simulation exercises would be counted towards your grading. And please finish it in 2 weeks' time. I would suggest that you start off right away so that you will not only just finish your assignment, but also you'll have a very good understanding of the subject, and that will really help you in your exams also. Okay. So thanks everyone. Have a nice day.
Thank you, sir.
Thank you, sir.